So up to this point, we still haven't answered the question of how do we know if a sequence is graphical or not. And this is what the Havel-Hakimi theorem addresses. So it says if S, so D1, D2, up through Dn is a sequence of non-negative integers, non-negative integers, such that, right, we'll assume, right, if it doesn't already look like this, this is sort of the bare minimum for being a degree sequence, that we can just reorder this in a non-increasing way, D1 greater than or equal to the rest, and so forth. So if we have some sequence that looks like this, is it graphical or not? And the Havel-Hakimi theorem, right, it doesn't directly address this question. It doesn't tell us yes or no directly. What it tells us is that this is a sequence. I'll say S is a sequence. Wait, how do I want to say this? The sequence S. The sequence S with this property is graphical if and only if this sequence is graphical. So that is, we take away D1 and we remove the rest. Oh yeah, we're also going to call D1 delta, just so I can conform with the book. D2 minus D1, and so we'll remove 1 from the next delta of these. The delta plus 1 minus 1, and then we would have the delta plus 2, not minus 1, because we just took away the first delta, and so on up through Dn. Graphical if and only if this is graphical. So, right, you might wonder how this answered the question of whether a sequence is graphical or not. It just told me it has to be graphical if and only if this other one is. The key thing here is that we reduced the number of vertices by 1. And so what this is going to do, this is going to give us a procedure that we continue to do this process of removing 1 from each of the first delta until we get a small enough sequence that we can just work out ourselves is graphical or not. One that we've already looked at. So for example, let's look at an example. Let's say our sequence S is 5, 3, 3, 3, 3, 2, 2, 2, 1, 1, 1. So n equals 11 here. So how do we know if this sequence is graphical or not? Well, what we do is we form the sequence S1 by removing 5 and decreasing each of the next 5 by 1. So it'll be 2, 2, 2, 2, 1. We used this idea in the last theorem. In theorem 1.11, we saw this come up. And then we'll reorder this. Maybe we call this one, what do we want to do? Let's call this one S1 prime. We'll reorder it. So I'll just write it as is 1, 2, 2, 1, 1, 1. And then our real sequence S1 would be 2, 2, 2, 2, 2, 2, 1, 1, 1, 1. So now we've reduced it by 1, n equals 10. So now we would have a smaller case to check, and we can just keep doing this. So we would form then the sequence S2 prime. I just take the first one away, this one goes away, and then I reduce the next 2 by 1, so 1, 1. And then I'll reorder it. I'm not going to bother drawing S2 prime, I'm just going to draw S2, which is the result after we reorder this and put it into non-increasing order. So that is, we're picking up 2 1s, and we just have these 3 2s left. So 2, 2, 2, 1, 1, 1, 1, 1, 1. And then we repeat the process. So now take away this 2. This is going to take, S3. This is going to take these down to 1, and we just have 1, 1, 1, 1. How many 1s do we have? We took away this one. 1, 2, 3, 4, 5, 6, 7, 8. 1, 1, 1, 1. So now we have a graph of down to order 8. Here n was equal to 9. And, well, now we ask ourselves, do we know a graph with this degree sequence of order 8? And we should be able to work this out. You can keep going if you want. But yeah, this isn't too hard to work out. It's a one regular graph of order 8. So you have to think, okay, how do I make a one regular graph? Well, every vertex has degree 1, so it's adjacent to every one other vertex. So it just seems like we just have to pair up vertices. So a graph like this, that is a matching. This is what we call a matching or a one regular graph. And so there's a one regular graph of order 8. And this, we can also go the other way, right? If we know this is graphical, then the next one up is graphical. So one, we know our original graph our original sequence is graphical now because we can go the other direction with it. So how do we go the other direction? How do we go from here to here? Well, you add a new vertex and make it adjacent to the next 2. So do, and now I have the one for order 9, right? This has 2, 2, 2. The rest are 1s. Where do I go from here? I'd add another vertex of degree 2 adjacent to 2 more vertices of degree 1. And then where do I go from there? So I added 1, 2. I added another 2. Add another 2. To 2 other vertices of degree 1. So how about over here? Now we're up to what? N equals 11. Now we're up to this one. So we have something with S1 as the degree sequence. Yep. Or sorry, we're up to N equals 10. We have this S1 as the degree sequence. And now look, we add a vertex of degree 5 to the vertices of degree 2. So vertex of degree 5 to the vertices of degree 2. 2. Two, 3, 4, 5. So there's one possible way to do that. And we get to the original degree sequence. Now we have a graph with that degree sequence. 5, 3, 3, 3, 3, 3. Right, just double checking. 3, 3, 3, 3. Oh, oops! No, I made a mistake. We need to do this to how many degree 3 vertices? 4 vertices of degree 3 and 1 vertex of degree 2. So maybe this one. So this is one way we can get a degree sequence. The book does it slightly differently, keeping the vertices the correct name. But this is certainly one way we can do it and go in the other direction to achieve a graph with that degree sequence. Okay, so why is Havel-Hakimi's theorem true? If we know this is graphical, how do we know this one's graphical? And what about the other direction? So again, proof sketch. Well, doing this thing I was just describing down here where we add a new vertex and make it adjacent to the rest, well, I can do that with this degree sequence S1. So if we assume that we'll do the backwards direction first. We'll assume S1 is graphical. Then add a vertex, and let's say this is vertex degree of V2. So let's say that corresponds to V2, V3, V4, up through Vn. Then add V1 to the graph and make it adjacent to each of these, V2, V3, up through V delta plus 1. So add in the edges to make it adjacent to these. Again, I'm just sketching this to, right, you can read through to get a more detailed and full sentences. Make it adjacent to these. And then, right, and then the new graph has a degree sequence D1, and then we added 1 to each one of these, D2, D3, Dn has degree sequence this, and hence the sequence is graphical, since there's a graph with that as its degree sequence. So is graphical. So that's how we do the backwards direction. And it's this exact process here of adding a new vertex and making it adjacent to the other ones. We can keep track of the subscripts to make this a little bit more rigid when we're doing that, but that works. And then the forward direction, so assume S is graphical. Then what we'll do is we'll use theorem 1.10. By theorem 1.10, there is a graph with neighborhood of vertex V1 equal to these ones, V2 up through V delta plus 1, and so on up to Vn. We can find some graph this with degree sequence S, right? We know there's some graph, since S is graphical, there's some graph that has this as its degree sequence. Theorem 1.10 tells us we can always select this graph that's nice like this with neighborhood of V1. I made a mistake here. This should just be up through V delta plus 1, right? We just want V1 adjacent to these. With this as the neighborhood of V1. And so what you do here is you just consider removing V1 from the graph. Then G minus V1 has degree sequence. So yeah, we took away the first vertex. This was the idea here. We took away the highest degree vertex, and we know since our graph, the vertex set or the neighborhood of V1 is adjacent to the next highest degrees, like this, we can just remove 1 from each of those, right? When we remove V1, we're removing an edge from each one of those. So that is G minus V1 has the degree sequence D2 minus 1, D3 minus 1, D delta plus 1 minus 1, D delta plus 2, and so on up through Dn, which is exactly what we wanted to show, that this is also graphical, right? So it's graphical. We found a graph with that degree sequence. And so that's the idea. We can follow this, right? This theorem is really establishing an algorithm that can be used to determine if a sequence is graphical or not. Again, start with the sequence and perform the same steps over and over again. this idea of removing the first one and decreasing the degree of the next delta by 1. Keep doing that until you get a degree sequence that you recognize. And also, right, so this one turned out to have a degree sequence. You can use this to show that a sequence is not graphical, right? Because this is if and only if. So you can also show this to show a sequence is not graphical. You would eventually get down to a sequence that you know isn't the degree sequence of any graph. All right, that's it for this one.